I'm looking at the preparation of benzene diazonium chloride from this chemical in the beaker, phenylamine or aminobenzene. In the beaker there I've got sodium nitrite dissolved in water, and in the conical flask I've got concentrated hydrochloric acid. I begin by adding the cooled phenylamine to the hydrochloric acid slowly. The reaction is exothermic, so to avoid producing fumes, I've cooled both of these reagents in advance. You'll see a precipitate is forming, but later when I add the sodium nitrite solution, this will go into solution. So slowly in stages, I add the cooled phenylamine to the cooled concentrated hydrochloric acid. You can see I've added it rather too fast there, and I'm getting fumes produced. Okay, having now added all of the phenylamine to the cold concentrated hydrochloric acid in the conical flask, I'm ready to begin adding the cold aqueous solution of sodium nitrite in the beaker. Now this really does need to be done slowly, keeping the temperature below 5 degrees C, because the product benzene diazonium chloride or phenylammonium chloride is unstable above 5 degrees C. There's the equation that shows that concentrated hydrochloric acid and sodium nitrite react to form nitrous acid, HNO2. Nitrous acid is an unstable acid and has to be made in situ in this manner. Later you'll see in the balanced equation, reacting with the phenylamine, I will show both hydrochloric acid and nitrous acid reacting to form the products. Now again, for the benefit of speeding up the video, I have added crushed ice in stages to keep the solution inside the flask below 5 degrees C. And at the bottom there you see the equation I referred to. We've got the phenylamine reacting with both nitrous acid and hydrochloric acid to form benzene diazonium chloride together with water. And that's what's happening in the flask right now. This did take several minutes, even using the crushed ice, and you can see that the video has been speeded up to about 3 times normal speed. The precipitate does go into solution as I add the aqueous sodium nitrite to the flask. And it took me about 5 minutes to add all of the cold aqueous sodium nitrite to the conical flask. Again, you can see I'm putting in crushed ice at stages. This is to keep the temperature in the flask below 5 degrees C. The heat of this exothermic reaction will of course mean that the temperature constantly tends to go up. And at this stage I've almost all of the sodium nitrite solution in. And the thing about this product, benzene diazonium chloride, is it's a great way of getting nucleophiles, electron-rich species, onto the ring, a ring that is electron-rich and will normally repel nucleophiles. So it's relatively easy to replace the N triple bond N attached to the ring with nucleophiles like OH to make phenol, a halogen to make chlorobromo or iodobenzene, or a CN nitrile group to form cyanobenzene or benzonitrile. And this all happens simply by warming the unstable phenyl ammonium chloride with an appropriate reagent. So I'm going to show just one example here. There is a second video that looks in a little bit more detail at the reactions of benzene diazonium chloride. But I'm going to show here 2 examples of coupling reactions, a process known as diazotization. You see at the top the equation there, and the product there with the N double bond N, that's referred to as the diazo link. So I've got here in the syringe some of my benzene diazonium chloride solution, and I'm adding it to a phenol solution in water with some alkali to help the reaction take place. And you can see that I'm getting an azo dye produced, yellow in colour. And this later can be filtered off using a Buchner apparatus to reduce the solid, which appears somewhat browner in colour than you see here. And over here on the right I have a beta naphthol solution, again in water with a little alkali to help the reaction, the coupling reaction or diacetization reaction. And this time you see we are getting a different colour of azo dye, reddish in colour. These azo dyes are referred to as chromophores, and in another video in this series you'll see that I look at chromophores and explain the origin of the colour. So two examples of the reactions of benzene diazonium chloride. Both are examples of coupling reactions. There's the solids collected afterwards that I placed in a desiccator to dry. The dish at the top has a mixture of the other two. There's a poster created with those dyes. You can see the red of the azo compound where I coupled benzene diazonium chloride with beta naphthol, and then that more yellow colour where I coupled benzene diazonium chloride with phenol. So that's been my look at the production of benzene diazonium chloride and a look at two of its coupling reactions. Please consider looking at the other videos in this series. And thank you for listening.